let's go ahead and get started. So, a little bit of housekeeping and talking about where we are in the semester and where we're going to be by the end. So, next week is going to be the week of July 4th, so we won't have class on Wednesday. I'm also going to cancel class on Thursday. So it's a good and a bad thing because that means that we only have 6 classes before the third exam. And looking at the schedule and where we are, we're not actually going to be able to get through all of the material that I would like, so some of it's going to be deferred to the final. But even still, there's not a lot of time for the things that we're going to be doing before the third exam, so make sure that you guys are on task. You ask questions if you have them, because, like I said, we're not going to have a lot of time. So the third exam is going to be not next Thursday, but the following Thursday. And it's going to be all about magnetic fields. And so as we're moving forward, what we're going to see is that the calculations that we do for magnetic fields follow fairly naturally from the things that we've already done with electric fields, with the exception that now we're going to have to worry about cross products. And the reason for that is ultimately the way that magnetic fields manifest themselves. So in previous chapters, when we were talking about electric fields, we know that an electric field just comes from some point charge like this. So if this is some plus Q, the electric field is just going to radiate away from this. Well, classically speaking, this is like saying that there's some source of electric field. So the electric field comes from here at a single point. There is no source for magnetic fields in the same way that you can write a source for electric fields. So one way to look at this is by looking at Gauss's law. So the integral of E dot ds is equal to Qn divided by epsilon naught. We should be pretty familiar with this equation. But something that this equation says very subtly is that there has to be some source in order for there to be some spread of electric field. There's an analogous equation. This is the second of Maxwell's equations that we don't really talk about very much. This is Gauss's law for electric fields. This is what's called Gauss's law for magnetic fields. And so what Gauss's law for magnetic fields says is that there are no sources of magnetic fields that are a point source. So what this means ultimately is in order to produce a magnetic field, you have to have some moving current. And so if this is some current here, then the magnetic field is going to go around like this. And so we can see in looking at this example of just this current carrying wire and seeing what the direction of the magnetic field is, you're going to have to do something to say the direction the magnetic field goes in this system is going to be perpendicular to this wire. So at every point, the magnetic field is perpendicular to the direction that the current is moving. So that's what's kind of leading us into the need that we have for the cross product. And so I just want to introduce the cross product in the way that I did in the notes and the way that you were meant to look at it on the homework. And that's to say that if I have two vectors, call this, this is the xy axis, call this the vector A, call this the vector B, there can be some angle in between them. We know if we wanted to find the dot product between these two vectors, that says that A dot B is equal to the magnitude of A times the magnitude of B times the cosine of the angle between them. And what the dot product tells us is that there's, the dot product tells us something about how parallel two vectors are. So if they're exactly in the same direction, the dot product is maximized. If they're perpendicular to each other, the dot product is going to be 0. The cross product, in a sense, is opposite of that. So when I say the vector A A cross B. This is equal to the magnitude of A times the magnitude of B times the sine of the angle between them times some unit normal vector n hat. Okay, so this portion right here versus this portion right here should seem to make sense, because what it says is the cross product is maximized when the two vectors are perpendicular. It's minimized when they're parallel. But then we also have this unit normal vector here. And the way that we go about resolving this unit normal vector is to apply what's called the right-hand rule. So everybody take your right hand. The way you apply the right-hand rule is to take the fingers of your right hand and point them in the direction of A, and then curl them into, you have to rotate your hand in order to do this, but you rotate your hand so that you can curl them into the vector B, and then your thumb is going to point in the direction of the unit normal vector. So in this case, what's the direction of n hat? So take right hand. This is the direction of A, curl into B. This goes into the board. Okay. So here we have some notation to talk about this. So this is in, and this is out. Okay. Is everybody okay with that? This is important. So if it's not, so one more time. Right hand, point fingers in the direction of A. I'm not really locked into I have my fingers pointing in the direction of A, but I can still rotate it however I want. And then I have to rotate it so that I can curl my fingers towards B. So curl towards B, thumb points in the direction of n hat. Is it okay? Yeah. Yeah, it really is, in the notation and the way it's said, it should be curl towards B, right? Curl towards B. Okay? We're going to get a lot more practice with this, but I'm just kind of laying it out in a very general sense right now. Okay, so where we're going to see this in practice, the first time that we're going to see this is in the Lorentz Force Law. So what the Lorentz Force Law says, the Lorentz Force Law gives you what the force is on a charge due to both an electric field and a magnetic field. And so we've actually already seen the first portion, right? F is equal to Q E vector. But the new portion is going to be plus V times, plus Q V vector cross B. Okay? So here's our first cross product that we have to evaluate here. And so for any problem that you have, if I want to find the direction that the force points, I have some charged particle moving with some velocity in the presence of some magnetic field. I take my fingers and I point them in the direction of V, and I curl them into the direction that B is, okay? Or curl them towards B, okay? So that's the Lorentz Force Law. We'll get more practice with that. I'm not going to go through that example here. And then the next equation that we have is what's called the Savart Law. Now, the Savart Law actually looks a lot like the equation that we had for finding the electric field from an infinitesimal charge, and that's to say that dE is equal to 1 over 4 pi epsilon naught dq divided by r squared times r hat. So this one, again, we're pretty familiar with. The Savart Law says dB is equal to mu naught divided by 4 pi times I dl cross r hat divided by r squared. Okay. So in practice, when we use this equation, it follows very similarly to the way that we use this one. The only real difference is, instead of talking about a charge, I'm talking about a current. And instead of saying that there's some r hat, I need to figure out what dl cross r hat is. Okay. Now, the example that I gave you here, it wasn't defined as well as I could have in the picture, and there's a simplification that I made that I should have stated more explicitly. So, in this example, I say that there's some current I that moves to the right, and this is the x direction, this is the y direction, and I want to find what the magnetic field is some distance y along the y-axis. And so, in order to do this, what I can say is that dl vector is going to be in the x hat dx direction because the current is going to the right. That's really what this dl tells you. When we're looking at current, we see that current's actually a scalar, right? This doesn't have any vector information with it. The vector information is going to come actually from the dl vector. So dl vector points in the direction the current is going to go. Now here's the part that I could have defined a little bit better. So I can draw the vector that points from this dl to the point of observation. This is going to be some r hat. This is r. This is a length of x. And so this is r hat and this is dl. I called this angle theta. This theta is not actually the angle in between dl and r, and we can see that even more if I do this. Here's r hat, here's dl, and what I did was I defined this angle theta. The angle in between these is actually this one. This is phi. Now, the reason why I can do that is because sine of theta is equal to the sine of phi. Okay? In this case. Okay? So really, I should probably go back and define this a little bit differently and then say instead go like this. Call this theta, call this dl. But you can see the reason why I did that and why I'm more interested in this angle than I am in this angle. And it comes down to the way that I'm going to represent it in terms of the ratio of the sides. Because I have a triangle here. I can play all of our games that we have with right triangles when I look at this, but I can't really do anything like that when I have this obtuse angle here. Okay. I'll go through this this calculation in a little bit more detail when we do a live stream tonight, and I'll do some more things with this equation. Okay. Any questions about this? I realized, like I said, that we're going pretty fast now because we don't have a lot of time left. But really, a lot of these things carry over from the things that we've done before. It's just a matter of understanding how to apply the cross product. That's really the new piece here. Yeah.
When you were deriving the Savart Law, I did not follow your talk about dimensions in the notes. Would you go over that briefly? You were saying the dimensions of length was involved, and I didn't.
Oh, right. Okay. Yeah. That was the other piece. So. Yeah, that had to do with the Lorentz Force Law and saying, okay, well, I can say for a point charge, the force on that point charge due to a magnetic field, if it's moving with some velocity v, is given with like this, right? Now, if I look at just this term here, this has units of charge times meters per second, right? Now, dimensionally, this term is the same if I do this, right?
All right.
Charge per second, yeah, exactly, times a meter. And really what this is just a current.
Yeah.
So I can rewrite this equation if I wanted to talk. This is just the force on a moving charge. So this is some q moving with some velocity v in the presence of a magnetic field. We can say it goes like this, right? But the whole reason why I'm doing this is because I want to be able to say something about if I have some current in a wire and I have some magnetic field going like this, what's the force on that wire? And so by following these dimensional arguments, I can rewrite this equation so that FB is equal to I L vector cross B. And now you might say that's kind of weird I'm writing an L vector, but it'll make sense why I'm doing that in a second. So this is true only if the magnetic field doesn't vary over the same variables as the length does. And so to write this more generally, what I can say is the infinitesimal force imparted on some infinitesimal piece of the wire is going to be equal to I dl cross B. Okay, and that was the piece I was getting at. Okay, other questions? Okay, so let's go ahead and get started on the work for today, and I'll come around and answer questions as you guys have them.